Hello everyone. Welcome to the fourth lecture in the course on reinforcement learning. I am Dhiraj Madan, and today we will be looking at the proof of Banach fixed point theorem. So in the last lecture, we had discussed the convergence of an iterative algorithm for computing the value function corresponding to a given policy. And we had shown that the particular iterative algorithm converges to the value function which is given by the set of Bellman equations, right? So that's what our claim was, right? And we had proved that this convergence happens using a fixed point theorem, and in order to do that, we had to show that the given mapping is essentially a contraction mapping. Right? So essentially, the mapping which we were given, which is given by V prime S, is Rs plus gamma times sum over S prime, P of S prime given S by S Vs prime. So this particular mapping from the initial value function B to the new value function B prime, we had to show that this is a contraction mapping. And then using the fixed point iteration theorem, we were able to show that this indeed converges to the solution of Bellman's equations. So that's what we had done last time. However, we hadn't proved the convergence of fixed point in general, right? We had just taken that theorem for granted. So today we'll study that proof in depth, and we'll also first build up some prerequisites in order to get to the proof of the given theorem. So let's get started. So today's video is actually an optional one, in the sense that you can skip this video without losing the continuity of the course. However, for those who like mathematics and who like who like to understand things in more depth, I would recommend them to watch this video. So let's continue. Okay. So yeah. So we were on the Banach's fixed point iteration theorem. So let me first state that theorem again. So let me write down. This is known as Banach's fixed point theorem. So let's see what it is. Although we have already applied this theorem earlier, but now let's see a proof of the theorem. So before going into the proof, I'll again state the theorem formally. So let T from Rn to Rn be a contraction mapping. Actually, the theorem is more general for arbitrary metric spaces. But since we are not going into the theory of metric spaces, so let's just consider it as a mapping from Rn to Rn. Okay. It is a contraction mapping, which means that is for all xy, we have the norm of tx minus ty is less than equal to c times norm of x minus, right? For some c less than. So there exists some c such that this condition is satisfied for all x. Okay. Or some constant c. So this c should not depend on x and y, right? It's a constant. Okay. Then there exists a unique x naught such that t of x naught is x naught, okay, which means that this is a fixed point, as in t fixes this x naught to x naught. Moreover, one can obtain x naught as the limit point of the sequence given by x naught, t of x naught, t of x naught, and so. Oh, sorry, x. Okay, we shouldn't start with x naught, right? Yeah. As the limit point of the sequence x1, okay, and then x2 is t of x1, okay, and then x3 is t of x2, which is t of x1, and so on. So basically, so here the sequence starts with an arbitrary point x1, and we apply and we obtain xn plus 1 equals to t of xn for all n greater than. Okay, so basically you start from some x1 and then you keep on applying t transformation. And this x1 can be any point, right? And you will always get to the limit point of the limit point which you will get to will be the fixed point of the contraction mapping T. Moreover, one can obtain x naught as one can obtain moreover for every x1, right? For every initial point x1, one can obtain x naught as the limit of this particular sequence. So whatever x1, whatever is the initial element you pick, you will always the limit of the sequence is always going to be x. So this is true for any arbitrary. So there are a lot of things to digest over there. Okay, so let's try to understand it. So T we are given is some contraction mapping, which means that whenever you take the sort of distance between Tx and Ty, it shrinks. Okay, so the distance between x and y, let's say whatever it was, now I'm looking at, I apply this mapping T to x and T to y, and the distance between them would have shrunk after applying this mapping, right? So the distance between Tx and Ty is less than equal to some constant times the distance between x and y. That's the assumption of the theorem. Okay, if this is true, then we say that this is a contraction mapping. And in this case, right, there exists a unique point x naught such that Tx naught is x naught, right? So that itself is a big statement. And not just that, the theorem gives me an algorithm to obtain that point. How? So essentially, let me start with some point x1 and I keep applying t. And essentially, the limit point of the sequence is going to be x naught. So whichever initial point I start with, the limit point is always going to be x naught. So first of all, the sequence is going to be a convergent sequence. That itself is a big thing. And then the limit point, right, the value which it converges to is same as that unique point x naught, which is Tx naught, which satisfies Tx naught equal to x. Right? So first of all, there exists such a point x naught. Secondly, it is unique. And thirdly, one can obtain it via this iterative algorithm. And this iterative algorithm, whichever point you start with, right, it's going to work. So that's the interesting part of the theorem. Okay. So let's try to prove this theorem first. Okay. So So first we show that T can have at most one fixed point. Okay. Let's say if not. Okay, let's assume to the contrary. If not, then there exists x naught and y naught such that Tx naught is x naught and Ty naught is y naught. Okay, so we are assuming to the contrary that let's say there are two such fixed points x naught and y naught such that for both of these we have Tx naught is x naught and Ty naught is y naught. Okay. Then what's going to happen is that then essentially Since tx naught is x naught and ty naught is y naught, so I can say that x naught minus y naught, the distance between x naught and y naught, the norm of x naught minus y naught, is same as the norm of tx naught minus ty naught, right? Because tx naught is x naught and ty naught is y. Now let's apply the contraction property. Now, since there exists a C such that this is less than equal to C times x naught minus y naught, so for that same C, you can just apply that property of contraction mapping to say that this is less than equal to C times x naught minus y. Right? And C is less than. Okay. Now, so what we have is that x naught minus y naught is less than equal to C times x naught minus y naught. And and C is less than 1. So is it possible? Right? So, or you can say that 1 minus C of x naught minus y naught is less than equal to 0. Since C is less than 1, 1 minus C is greater than equal to 0. This is also greater than equal to 0. So what this would mean is that x naught minus y naught, this distance is 0. And by the property of norm, which means that x naught minus y naught is 0, or essentially x naught is equal to 1. So if at all there is a fixed point, it must be unique, right? So if there are, even if we assume that there are 2 points x naught and y naught, then essentially we get that x naught must be equal to 1. If the 2 points, both of them satisfy tx naught is x naught and ty naught is y naught, then x naught must be equal to 1. Okay. Now let's come to the existence of this fixed point. So how do we prove this existence? So actually we'll again take that iterative approach only. So let's say we start with the sequence. Okay, so let's start with some arbitrary x1. Okay. So let x1 be arbitrary. Okay, so I've started from some arbitrary x1. Okay, and now we consider the sequence x1, okay, and then x2 is t of x1 and so on, right? X3 is t of x2, which is t of x1 and so on. So in general, xn plus 1 is t of xn for all n greater than 2. So we start with this particular. Let's look at this particular sequence. Okay. Now our claim is that this is a Cauchy sequence. So as an interlude, I'll just give you some more prerequisites which we need about this theorem. So let's take an interlude. So let's I'll just cover 2 definitions. So first is the definition of a convergent sequence, right? When we say that or limit of a sequence. So a sequence x1, x2, so on, dot is convergent if there exists some x such that for all epsilon greater than 0, whatever small epsilon you pick, there exists some n naught, okay, such that the distance between xn minus x is less than epsilon for all n greater than equal to n. So this is the definition of convergent sequence. And here x naught or x is the limit of the sequence xn. And we can write it as xn converges to x. So whether we write xn converges to x or we say x is the limit of the sequence xn, these are one and the same thing. If there is such a limit, then we say that the sequence is convergent. Okay, so what does this mean that x is a limit? It means that whatever small epsilon you pick after some value n naught, essentially all the points are going to be close to x, okay, with distance less than epsilon. So that's what we mean by a convergent sequence. And I'll give you another definition, which is the definition of Cauchy sequence. Okay. So a sequence, let's pick some new color. Okay, let's pick, okay, black we haven't used, right? For some time, let's use black. So a sequence xn, n from 1 to infinity, is Cauchy. Okay, if for all epsilon greater than 0, okay, there exists an n naught, okay, such that for all mn greater than equal to n naught, we have that norm of xm minus xn is less than epsilon. So this is the definition of a Cauchy sequence. And note that every convergent sequence is Cauchy. Why is it so? Because there will be some n naught after which all the points will be close to the limit point with a distance less than epsilon by 2. So therefore, the distance between any 2 points after that n naught is going to be epsilon by 2 till the limit point x, and then epsilon by 2 till the other point xn, right? So just prove it. So I'll leave it as a homework exercise. Yes. And we also have a definition that if every Cauchy sequence is convergent in a non-linear space, in a normed vector space, then it is called a Banach space. So actually, I could have talked about this in terms of metric spaces also. Then we could have called it a complete metric space. But since we are always talking about norm here, and that's what is of concern to us, so I'll talk about norm vector spaces. So if in a normed vector space, we have that every Cauchy sequence is convergent, then it is called as a Banach space. So in the so the norm which we will be talking about will be the sub norm, wherein we'll wherein we'll actually be having a Banach space, right? So okay, and here the assumption is that if vector space Rn with this particular norm is a Banach space, meaning that every Cauchy sequence is convergent, then there exists a unique x naught such that the x naught is x naught, and one can obtain x naught as the limit point of the sequence. So until now, we didn't have to make this assumption, but for the existence and for the convergence of the sequence, we need this assumption that every Cauchy sequence is convergent. Another way of stating that is that this is a Banach space. Okay. Okay. So this was an interview. Okay, so now this is over. So let's get back to our proof. So we started from the sequence x1, x2, x3, and so on, right? And we were given that which is obtained by applying t repeatedly. Okay. So now this interlude is over. So we are now back to proof. So let's discuss the. So my claim is that the sequence x1, t of x1, t of x1, this sequence is a Cauchy sequence if t is a contraction. Okay. So how do I show that this is a Cauchy sequence? So let's try to do this. So suppose okay, so basically what we need to show that after some interval n naught, so the distance between xm and xn will be less than epsilon. Okay. So how do we now show that? So essentially, so suppose let's say m is greater than n. Okay. And now let's look at the value of distance between xn and xn. Okay, so now let's try to compute this distance. Now xn minus xm, actually I can take m to be greater than equal to n. Okay, now I'm now looking at distance between 2 points first, which is xn and xn. Now, how do I obtain xn? So I start from x1 and I need to keep applying that mapping t. How many times will I need to apply it on x1 to get to xn? N minus 1 times, right? Because if I start from x1, if I apply once, I'll get to x2. If I apply twice, I'll get to x3. If I apply n minus 1 times, I will get to xn. Similarly, xm is t of m minus 1 acting on x1 on this particular node. And now what I do is that essentially I can rewrite this as, now this is equal to, okay, okay. So essentially when I say that this is t of n minus 1 acting on x1 and t of m minus 1 acting on x1, so essentially since t has been acting n minus 1 times and t has been acting m minus 1 times here, and we know that n is smaller, so what I do is that I can rewrite this as this is less than equal to gamma times t acting on n minus 2 x1 minus t acting m minus 2 times on x. Because essentially, what is t acting n minus 1 times? So basically, this is t acting n minus 2 times on x. Right? So I just open this up. So essentially, and then I use the property of contraction mapping. Okay, this is not gamma, this is c. Right? Because in general, we are using the variable c. So gamma, that specifically discount factor, that came just for Markov decision. So by the property of contraction mapping, okay, let me rewrite more detail. So essentially, this is equal to t acting n minus 2 times t acting n minus 2 times on x1 minus t acting m minus 2 times on x. And essentially, now I apply the contraction property on tn minus 2 x1 and tm minus 2 x1, and I get that this is less than equal to c times the norm of tn minus 2 x1 minus t m minus 2 x1. Okay. So again, if I apply that property, I'll again get a c, and this will become n minus 3, and so on. So how many times can I get this thing? So essentially n minus 1 times I can take the c out. Okay, less than equal to c acting n minus 1 times c to the power n minus 1 on distance between x1 and t m minus 1 minus n minus 1 x1, which is t m minus n x1. So this is something I can write. Now, how do I compute this distance? Okay. So what I do is that I rewrite this as c to the power n minus 1. And now I write it as x1. Okay, by the way, tm minus n acting on x1 is just how much? X m minus n plus 1. So this quantity is nothing but x m minus n plus 1. Okay. And so this is x1 minus xm minus n plus 1. So I write it as x1 minus x2 plus x2 minus x3 plus so on, and then plus xm minus n minus x m minus n plus 1. So I rewrite it as this telescopic sum. Okay. Now I apply triangular inequality on these pairs of differences of pairs. Okay, so this is less than equal to Cn minus 1 on multiplied with norm of x1 minus x2 plus norm of x2 minus x3 plus dot 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 norm of xm minus n minus xm minus n plus 1. So this equals c to the power n minus 1. Okay. And now what I have is distance between x1 minus x2. Okay. And now x2 minus x3 is essentially again just tx1 minus tx2. So that is less than equal to, okay, so I'll write it as tx1 minus tx2. Okay. And then what I have is x3 minus x4, that will be t of x1 minus t of x2. And then t of x1 minus t of x2. Okay. And so on until xm minus n plus xm minus xm minus n plus 1. Okay, so that will be t acting how many times? M minus n minus 1 times on x1 minus t m minus n minus 1 of x2. So when I say t to the power m minus n minus 1, it means that t applied on x1 these many times. Okay. And now I again use the property of contraction mapping to show that this is less than equal to norm of x1 minus x2 plus c times the norm of x1 minus x2 plus dot 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 until c to the power m minus n minus 1 of norm of x1 minus x2. And now this is a geometric sequence. Okay, and c is less than 1. So we know that this geometric sequence is upper bounded by c to the power m n minus 1 times x1 minus x2 over 1 minus c. Okay, because if I carry it out till infinity, then I'll get this ratio of 1 over 1 minus c, since this is terminated finitely. So I can always say that this is less than equal to c to the power n minus 1 over 1 minus c. Okay. So essentially, so given any epsilon, so basically we have said that xm minus xn is less than equal to c to the power n minus 1 x1 minus x2 over 1 minus c. Okay. And now if I choose essentially n naught such that c to the power n naught minus 1 times norm of x1 minus x2 over 1 minus c is less than epsilon. Right? So since this is an exponentially decreasing term, so essentially I can always pick some n naught such that this particular ratio is less than epsilon. And essentially in that case, what I'll get to is that essentially then for all mn greater than equal to n naught, we have that xm minus xn is less than epsilon. So essentially we have proved that this is a Cauchy sequence if T is a contraction mapping. Now, if the vector space Rn under this norm is a Banach space, meaning that every Cauchy sequence is convergent, then the sequence xn and from 1 to infinity is convergent. okay, which means that there is a limit point. And let xn, let the sequence converge to the point x. Okay. So what does that mean? So that means that so what our goal was to be able to show that there is a fixed point, right, and it converges to fixed point, right? So until now we haven't shown that tx equals x, right? So whether it is a fixed point or not. So we have shown that this is a convergent sequence because it is Cauchy. But now how do we show that this converges to the fixed point of t? Okay. So let xn converge to x. Okay. Then given epsilon greater than 0, so there exists n naught such that norm of xn minus x is less than epsilon for all n greater than equal to n. Okay. So if I apply again that property of contraction mapping, what I'll get is that txn minus tx, okay, this is less than equal to c times the norm of xn minus x, which is less than c times epsilon for all n greater than equal to n naught. Okay, because if for all n greater than equal to n naught, xn minus x is less than epsilon, then txn minus tx by contraction property, it should be less than equal to c times norm of xn minus x. And that should then be less than c times epsilon for all n greater than equal to n, right? And c is less than 1. But what is t of xn? So by the definition of the sequence, t of xn is nothing but xn plus 1. So xn plus 1 minus tx is less than equal to c times epsilon for all n greater than equal to n naught. Okay. So which means that whatever epsilon I pick, okay, so xn plus 1 minus tx for all n greater than equal to n naught, this is less than equal to c epsilon. So which means that for all n t greater than equal to, let's say, n naught plus 1, what I have is that xn plus 1 minus tx is less than equal to c epsilon, which is also less than epsilon because c is less than 1. So which means that the sequence xn, okay, so n is greater than equal to n naught plus 1, so then I can take it to be xn. Means that this sequence xn also converges to tx. Right? So basically the sequence xn converges to x and the sequence xn also converges to tx. But we know that a given sequence can have at most one limit point. It can converge to at most one point, right? So therefore, tx must be equal to x because any sequence can converge to at most one point. So therefore, we have that tx must be equal to x. So we have shown that, okay, so this has actually also proven that t has a fixed point, right? It was not very clear earlier, but by taking this iterative algorithm, we have shown that firstly this iterative algorithm converges. The sequence does converge to a point, the limit point, and essentially that limit point must have tx equals to x. And in order to show that, we again use the contraction property. Okay. So let's just revisit the proof. Okay, what did we do until? So we took the sequence x1, x2, and so on, where xn plus 1 is just t of x. So first we showed that the sequence is Cauchy. How did we show that? We took two arbitrary elements. We took the distance. In order to compute the distance, an upper bound on the distance, we use the property of the contraction mapping. And we show that the distance is upper bounded by cn minus 1 over c times x1 minus x2 if m is greater than equal to n. So if m and n, I choose them to be greater than equal to n naught, so essentially I can choose an n naught such that this distance is upper bounded by epsilon. that shows that the sequence is Cauchy. By the property that this is a Banach space, meaning that every Cauchy sequence is convergent, we can show that this particular sequence must have a limit point. Let that limit point be x. Okay. And now we show that, okay, if the limit point is x, then tx must also be a limit point, right? Why is it so? Because, after some distance, after some point n naught, so distance between xn and x must be less than epsilon for all n greater than equal to n naught, right? But then I have shown that if I take, the next element xn plus 1, from then onwards, the distance must be distance between xn and tx must also be less than equal to some epsilon, right? So whatever epsilon I pick, okay, so after that n naught plus 1, if I take, then the distance between tx and the sequence elements of the sequence is also less than epsilon. So and then by the property of uniqueness of limits, we see that, okay, the x was also a limit and tx is also a limit. So how is it possible, right? The limit must be unique. So then we get that tx must be equal to x. Okay. So therefore, the limit exists. Not just it exists, it must satisfy tx equals to x, and that gives us a proof that the t must have a fixed point. And see, this is a sort of a result in mathematics, right? And which has nothing to do with reinforcement learning, but essentially in the proof or showing the convergence of iterative algorithm for policy evaluation, this result was being used. Right, and this also shows that the system of equations in MTP that has a unique solution, that has a solution, and the solution is also unique. So it guarantees existence and uniqueness of solutions, as we had shown by applying this theorem in the last lecture. So this was mostly an interlude. So I hope you enjoyed this lecture. I would maybe, if you didn't understand it fully, you can watch it again if you find it interesting. Otherwise, it doesn't break the flow or the continuity of the course. So feel free to watch the remaining videos. In the next lecture, what we'll do is that we'll study an algorithm to see how to maximize, to see how to select the policy which maximizes the given cumulative reward, right? So that will be the actual value iteration and policy iteration algorithms, which we'll see in the upcoming lectures. So until now, we had seen how to evaluate a policy, but now how to maximize the value function with respect to the policy. That is something which we will see in the next upcoming lectures. Okay. So I hope you enjoyed this lecture. Okay. So and to continue to watch the remaining videos. And once we are done, then we'll move on to actual reinforcement learning as well, right? Wherein this environmental law is not known, then we'll see what happens. Okay, so okay, goodbye, take care, and see you in the next lecture. Bye.